Hello everybody, welcome back. Today we're going to talk about type 1 and type 2 errors and a concept in statistics called power. And this is going to be from chapter 9.1 and 9.3 of our textbook. And our objective for today is to interpret the power of a significance test and describe what factors affect the power of a test. All right, so first of all, we're going to talk about the probability of a type 1 error. And in this box here, it says the probability of making a type 1 error in a significance test is equal to the significance level alpha. So if you have an alpha of 0.05, let's say, that is going to correspond with your type 1 error probability. So the probability that you reject the null hypothesis when the null is actually true is 0.05. So let's revisit this table here that we first looked at when we started discussing type 1 and type 2 errors. And again, just to recap, a type 1 error is when you reject the null hypothesis when the null is actually true. And a type 2 error is when you fail to reject the null hypothesis when the null is actually false and your alternative is true. Now, this portion here, or this part that's circled in red, is what we refer to as power. And there are a lot of different ways to think of what power is, and I'll give you a few different ways because it's a tricky concept to understand. But I'm going to try my best to clarify it for you. But according to this chart, as you see, it is rejecting the null hypothesis, correctly rejecting the null hypothesis, when the alternative hypothesis is true. So it's just our ability to correctly reject a false null. Okay? So that's what we call power. This down here, there's no term for that, but each of the other three parts of that table do have a name. This, just put a happy face here. There's no name for that. That's correct. It's a correct conclusion to fail to reject the null when the null is true, but there's no name for that. All right. So here's some things to think about here. So we can decrease the probability of making a type 1 error in a significance test by using a smaller alpha. Because remember, if you set your alpha, let's say 0.01, you're lowering your probability of a type 1 error. But we have a trade-off. There is a trade-off between a type 1 error and a type 2 error. There's an inverse relationship. Now, some books will call type 2 errors as beta. Okay, so I'm going to go ahead and use that notation just to hopefully simplify things. But alpha and beta are inversely related. So if say your type 1 error goes down, if your alpha goes down, you're actually increasing your probability of a type 2 error. Your beta would go up. Okay? So it says down here in the last box, if we make it more difficult to reject H naught by decreasing alpha, we increase the probability that we will not find convincing evidence for the alternative hypothesis when it's true. Okay? So keep in mind, type 1 errors and type 2 errors are inversely related, and there is a trade-off. Sometimes getting a lower type 1 error may not be worth the type 2 increase. All right, so now back to power. So the power of a test, is the probability that the test will find convincing evidence for the alternative hypothesis when a specific alternative value of the parameter is true. Okay, this is the definition in our textbook. Just keep in mind, so when you're trying to find the power of a test, we usually have a specific alternative value of our parameter in mind. We are not going to directly calculate power, and neither will we directly calculate a type 2 error. We will usually be given one or the other. Calculating a type 2 error or power on their own is beyond the scope of this class. But we will get either the type 2 error or the power, and I'm going to show you a connection between those two ideas. All right. Now, again, power is a difficult concept to grasp, but here's some other ways to think about power. Okay, so all of these are fine. A test's ability to detect a false null hypothesis is one way to think about power. You can also think of it as the probability of correctly rejecting a null when it's false. It's also the probability of avoiding a type 2 error. All right, so let's take a look at this example here. And I'm going to let you guys read through it on your own first, and then I will highlight some of the more important ideas here. So go ahead and pause the video and read it, and then come back with us in about a minute so we can discuss how to solve this. Okay, so we have a null hypothesis with a mu equal to 30 and an alternative hypothesis with a mu greater than 30, where mu is a true mean lifetime in hours of these deluxe AAA batteries. All right, now let's get down to the question. The power of the test to detect that mu equals 31, there goes your specific parameter value, mu equals 31, is 0.762. Again, calculating power is beyond the scope of our course here, so they'll usually give you that power value or they'll give you the type 2 error probability. So that's 0.762, and we're going to interpret what that means. All right, so this is our interpretation of power. So please copy this down and you can use this as a frame here. So if the true mean lifetime of the company's deluxe AAA batteries is mu equals 31, so if that specific alternative parameter value is true, there is a 0.762 probability that the company will find convincing evidence for that alternative hypothesis. Specifically, mu is greater than 30. Okay, so that is the way we interpret power. All right, so relating power and type 2 error. So let's start up here. So it says in the previous example, the probability that we reject the null, given that mu is 31, so we are correctly rejecting a false null, the probability is 0.762. Now, remember, a type 2 error is failing to reject the null when the null is false. So the probability that we fail to reject the null when mu is actually 31 is going to be the complement of this event up here. All right, so if you take the complement of the probability that was calculated up there, you get 0.238. Okay, so this was our power probability. And down here, this is our type 2 probability. So what I wanted to illustrate here was that power and type 2 error are complements of one another. So if you have the probability of a type 2 error, all you need to do is subtract 1 from the type 2 error to get power. And if you have power, you can subtract 1 from power to get the probability of a type 2 error. So like I said, calculating power directly or type 2 error directly is a very detailed calculation that goes beyond the scope of our class. But you will usually get one or the other, and you'll easily be able to find one given the other. So let's try that out on the resulting sides. Actually, I'm sorry, one more thing before we get into an example. So, very important, increasing the power of a significance test does involve, or can involve, these three ideas here. Okay, so what can researchers do to decrease the probability of making a type 2 error and increase the power? So how can we decrease type 2 and increase power? Because in general, you do want to have a test with a lot of power. Now, there's three things that you can do. And one is make the sample size larger. Okay, that will increase the power of your significance test. You can make the significance level alpha larger. Okay, so one other thing I did want to mention is, so your alpha level, so when alpha goes up, power goes up. Okay, so When sample size goes up, power goes up, and likewise with alpha going up, power will also go up. So actually when your type 1 error probability goes up, your power will also go up. And the third thing you can do to increase the power of a significance test is to make sure that the null and alternative parameter values are farther apart. Not that you can make sure to do that, but that is another way to increase the power of a significance test. All right, here's a meme that may help you remember one of those three things. I heard you upped your sample size. More power to you. Ha ha ha. Right, sample size went up, so power goes up. All right. This problem here, it says we had an Alzheimer's experiment we talked about in a previous example or in a previous lesson, and it was about users of a new drug experiencing less nausea. So we had a null of 0.10 and a alternative of p is less than 0.10. Now, I'm going to pause. I want you guys to pause the slide and just read through it, and then we're going to answer these three questions down here. Okay, so we're going to look at these three letters down here, and we're going to see what of these changes would either increase or decrease the power of our test. Okay, so on the part A, you'll notice we're going to decrease alpha. Alpha goes down, okay? And then on part B, you may notice our true parameter value is going to be further away from this value over here, 0.10. 0.10 to 0.6 is a further, much bigger distance as opposed to 0.10 versus 0.8. And then in C, we are going to use a lower sample size, n equals 200 instead of 300. So here, for part A, you are going to decrease your power, because when you decrease alpha, you decrease power. Okay, so using a smaller significance level makes it harder to reject the null when the alternative is true. When the alpha goes down, your power goes down. In part B, power is going to increase. And when your parameter value is further apart from that null value, if there's a bigger difference between the null and alternative parameter value, you're going to get that increase in power. And for part C, remember that a smaller sample size, there's a direct relationship. Sample size goes down, then power will also go down. Okay, so one last thing before I let you go. So here, I know the multiple choice section of the AP exam is canceled, but here is a previous problem that has been asked before. Now, typically, power, again, very challenging concept to understand. They don't really go in depth. They sometimes give a multiple choice question on it. Sometimes it makes an appearance in the FRQ, so we just have to be prepared for it because you do have an FRQ only AP exam this year. So it says here, suppose that on a hypothesis test for a single population mean, the alternative hypothesis is mu is less than 10. Assume that HA is true. For a fixed sample size and significance level alpha, the power of the test will be greatest if the actual mean is which of the following. So we want here to look for the null and alternative parameter values being the furthest apart in the correct direction. Okay, because again, we're assuming HA is true, that the mu is less than 10. So that knocks out a few of our answer choices. Okay, only leaves you with these two. And you want, again, the null and alternative parameter values to be the furthest apart in the correct direction. That gives you an answer of 8 being A. All right, if you guys have any questions, please do not hesitate to send me a message on Google Classroom or Schoology. And hope you guys have a great day.